Cool. Hi, guys. So just a quick introduction about me. My name is Ryan, and I've got into all this crypto stuff from doing CTF challenges in high school. I was kind of a mathsy nerd in high school, and so this crypto kind of stuff really resonated with me. And I hope through our journey today, I can show you why I think crypto is cool and maybe make you interested in cryptography as well. Okay, so let's start. Have you ever noticed at the start of a WhatsApp message, it says, messages and calls are end-to-end encrypted. No one outside of the chat, not even WhatsApp, can read or listen to them. And so this kind of seems like black magic, right? Because on the one hand, WhatsApp is able to store your messages and send them to your friends, and it probably has like a whole server full of your messages. But at the same time, WhatsApp can't read your messages. So let's have a look at how this works, because this is important to understand why your messages are secure and whether they really are secure. So if we have a look at the website, it says, before a message ever leaves your device, it's secured with a cryptographic lock, and only the recipient has the keys. Well, what keys? Like, if I'm receiving a WhatsApp message, I'm not holding some keys. Well, it's not talking about physical keys. It's talking about cryptographic keys. So when you send a message, there's this thing called a private key, which allows you to encrypt your message. And on the receiving side, only the recipient has the private keys, and this allows them to decrypt the message. And so this sort of system is really important in the real world for stuff like communicating over a public channel. So if you're talking to your friend over the internet, you don't want anyone on the internet to be able to hear what you're saying. Or like if you're making an online payment, you want to send your card details to whoever you're buying stuff from, and you don't want anyone else to know what your card details are. And so let's have some sort of intuition for how this works. Let's say again that I'm Ryan on the left, and I'm trying to talk to Cyril in the middle, and I'm trying to say a secret message without WhatsApp on the right hearing. And so, say Cyril knows how to translate from English to Parser. This is a way he can allow people to talk to him. So he will publicly announce, here's how you translate from English to Parser. And so this means that I guess both me and WhatsApp and anyone else listening can translate from English to Parser. And so me on the right, I'm here, and I want to say WhatsApp is smelly, but I don't want WhatsApp to hear this. So red is going to indicate that this is my secret message. And red, I guess, indicative of being dangerous if you send this message publicly. I don't want to speak this out, so this is what I'm thinking right now. But since I know how to translate from English to Parser, I will instead say gibbity gobble goop in Parser. And this is in green because this is safe to send across the internet. This is like your encrypted message. And this means that even if WhatsApp hears this message, it has no idea what this is. So Cyril on the receiving end is hearing the message. And because Cyril can translate from Parser to English, but no one else can, he is able to translate it, and he knows that I'm trying to say WhatsApp is smelly. And throughout this whole process, WhatsApp can hear, WhatsApp over here, can hear what the message is, and can also translate from English to Parser, but only Cyril can translate from Parser back to English. So WhatsApp doesn't know what the English message is. Does that example make sense? Well, this message over here, I had taken, the image I've taken from how to deal with people talking behind your back from WikiHow. Very relevant. And let's see what WikiHow says about this. Well, it says do nothing because WhatsApp can't do anything about this. It has no way of telling what the actual message is. Let's look at how we can apply this sort of cryptographic algorithm in the real world. we require some sort of hard problem. And by hard, we mean it would take too long to compute, even if you had like all the computing power and all the time in the universe. And this kind of means that like even if you try to crack it, you won't be able to. So an example of a hard problem is factorization. So given a really large number, like this number, for example, we want to try to factor it. And I claim that there's no easy way to do this. A naive way to try to factor it is, I guess, trying to divide by every number. So we can try dividing it by 2. That's not going to work because this number is odd. And we can try dividing it by 3. And this isn't going to work either because it has a remainder of 1. And I guess we can try dividing it by every number, right? Trying to get the remainders mod all the numbers from 2 all the way up to 4 gazillion. And I guess this is one way to guarantee that you found the factors. And even if you do some optimizations, I guess one simple optimization would be that since you divided it by 2 and it's not divisible by 2, you shouldn't try dividing it by 4 because it also won't be divisible by 4. But I claim that even if you have some sort of optimizations like these, 4 gazillion will still be a really big number to try to crack, and you just need to try a lot of factors. And the reason why this works well is because, like, if you know 2 really big numbers, you can multiply them easily. You just multiply the first digit, move the carry, multiply the first digit with the second digit, and I guess like the normal multiplication algorithm. That's like really easy to do. You've done that as a child. But given a really big number, it's non-trivial to see that this 4 gazillion factorizes into these 2 smaller numbers. And so this sort of thing means that you can go in one direction really easily, the direction of given 2 smaller numbers to multiply it to get a big number. But it's really hard to go in the opposite direction, where given a really big number, find the smaller factors. And this is kind of analogous to tangled earphones. I remember in high school, I used to have wired earphones. I put them in my bag, and when I took them out, they were always tangled without fail. It was really annoying because it gets tangled really easily. You barely have to do anything to it. But at the same time, if you try to untangle it, it's really tedious, and there really isn't a quick way to do this. And so I guess this is modern cryptography. Modern cryptography relies on this sort of factorization problem being hard. And if you have heard of stuff like RSA or Diffie-Hellman Q exchange, this relies on factorization and a few other problems being hard to crack. But let's look at something more cool. So this is XKCD. It's a comic for nerdy comp sci people like myself. And you can see in the top right as quantum, which is both hard to understand and philosophically exciting. So let's talk about quantum computing. So I guess with sufficient advances in quantum computing, factorization becomes not a hard problem. If you chuck enough qubits at it, you just kind of solve it. And note that quantum computers aren't good at solving every sort of problem. It just happens that factorization is one of the problems it's good at solving. And so we need to find alternatives to modern cryptography, because with factorization being an easy problem to solve, then our modern algorithms will be easily cracked, and everyone can read your DMs. So let's look at a category of problems which is hard for even quantum computers to crack. Well, it needs to be hard for both modern computers and quantum computers. And this is a sort of problem, which is good. So this is a 2D lattice. It's a grid of points, and it extends infinitely in all directions. I guess it's regular like this. And it's 2D because it's on the screen, it's not sticking out. And a lattice can be defined by its basis. Its basis is 2 arrows, or some collection of arrows. And this basis defines the lattice because from any point to get to any other point, you can follow the arrows from head to tail So in this case, you're trying to get from this point to this point. I'm following these arrows backwards and then these arrows forwards. And I claim that you can get from any point on your lattice to any other point on your lattice by following arrows like this. And this means that our basis defines our lattice. Note that there's also other bases that define the same lattice. Like for these two arrows here, you can also follow them head to tail in any order you want to get from any point to any other point. There's many bases for each lattice. There's actually infinitely many. And I'm going to say there's two classes of bases. There's the nice ones, and the nice ones are these. It's nice because the bases are as short as possible, and there's a few other properties required for it to be nice. And I guess these aren't nice because the arrows aren't as short as possible. So there's this class of problems in lattice called a closest vector problem. And so this is saying that given any point on your lattice, any point doesn't have to be on your lattice. So in this case is our green point. We want to try to find the closest point which is on the lattice. And in this case is the red point. And doing this problem is hard in higher dimensions because I guess an intuition could be that your green point has a few points like around it. It has these 4 points that you could possibly check. But in high dimensions, the number of like close candidates grows exponentially, and it's not feasible to check them all. If you just take my word, that is hard in high dimensions. With classical computers or quantum computers, this can be the start for an encryption algorithm. However, if you have a nice basis, so in this case, it's this nice basis, you can find the closest point easily. If you don't have a nice basis, such as the one I showed before, you can't find the closest point easily. So like here we have our green point, and because the basis is not nice, we don't have red point because we can't find it. And so with a nice basis and a not nice basis, I guess this kind of thing hints at what we can have as a private key and a public key. So let's say, again, that I want to tell Cyril a message without WhatsApp hearing, but now WhatsApp is this like super good quantum computer guy. So instead, Cyril needs to do something with lattices so that WhatsApp can't understand it. So not WhatsApp. Cyril is going to announce a basis. He's going to announce a not nice basis. And this describes a lattice. So everyone knows what lattice we are working with, and everyone has a not nice basis that represents this lattice. I want to send this point, which is our red point, red being the secret message. And note that messages don't necessarily have to be strings. Like strings are kind of overrated. You can send any sort of information, and that will be enough to prove that you can communicate secretly. So if I want to send this point on this lattice, I don't want to send the point itself, that's the secret message. I want to encrypt it in some form. So I'm going to move this point a little bit, and I want the closest point to still be the red point. So I'm going to move it here. It's like moving it just a little bit. And so if someone were to figure out the closest lattice point, they would find my secret message. So this is my encrypted message, and this is what I tell to Cyril. Note that I'm announcing this so everyone can see what my encrypted point is. On Cyril's side, he is trying to decrypt my message. He has the green point, and he wants to find the closest point, which is on the lattice. He does this by using the closest vector problem. And because he has a nice basis, this is easy for him, even in high dimensions. And note that only Cyril has this nice basis. And so without much effort, he can find the closest lattice point. However, note that even if WhatsApp has the information of your not nice basis, and it knows what your green point is, it can't recover the red point because This is like solving the closest vector problem without init spaces. And so I have successfully towed my red point to 0, which still can't be cracked by a quantum computer. But wait, this algorithm can actually be cracked. It's called the GHH algorithm. And I think in 2007, it was cracked by Shamil. And this goes to show that it's really hard to show that something is cryptographically secure. Even if the class of problems you're working with is hard to crack by a quantum computer. And there's other cryptographic schemes which haven't been cracked, even with a quantum computer. But I haven't chosen to go through it because they're more advanced and less intuitive to explain. Well, nonetheless, the whole black magic behind all these cryptographic systems is for some sort of process to be easy to go in one way, such as multiplying two numbers or shifting a point to get a non-lattice point, but hard to go in the other direction, such as factoring a number or getting the closest point given a non-lattice point. And so I hope this has made you interested in cryptography. Here's some sources I've used, and people have also said that Math 3411 is a good course. So thanks for listening.